All right, so in this video, we're going to look at how to find the interval and radius of convergence for power series. Now, there's essentially three kinds of scenarios where your power series will converge. So option one is that it converges only at a single point. Option two is that it converges everywhere. And then option three is that it converges at an interval of finite length. And so we're going to look at each one of these cases in turn. Now, often the converges at a single point and converges everywhere are considered special cases. They aren't the most common things that prop up, but they do occur and you do need to know how to deal with them. They are in some ways easier because you don't have any endpoints to check. But when the function or the power series converges at an interval that is not all real numbers and is not a single point, then you have to worry about whether or not the endpoints are included. And so that takes a few additional steps. So we have three examples here, one of each type. And so we're going to go through and analyze them one at a time. Now, in the first case, sometimes these kinds of examples are easy to miss. And the reason for that is because when you do the limit of your, using your ratio test, it initially looks like it's not going to converge anywhere. So let's actually run through our ratio test for this example. Now, for some of these problems, you can use either the ratio or the root test, but with the factorial, it's a little easier to just use the ratio test. Now, recall that our ratio test is going to be the limit as n goes to infinity of the n plus first term, so n plus 1 factorial, x to the n plus 1 divided by 5 to the n, and then divided by the original term. I'm going to skip a step and multiply by the reciprocal. This should be n plus 1. And then the reciprocal would be 5 to the n over n factorial x to the n. That isn't quite what I wanted. Fine. There we go. Absolute value. Really expected it to resize, but what have you. All right, now when you simplify this, the 5 to the n and the 5 to the n are going to cancel, and you're going to end up with 1 5 left over. When you simplify the factorials, n plus 1 factorial is n plus 1 times n factorial. So the n factorials are going to cancel. And likewise, the x to the n plus 1 is going to cancel with the x to the n, leaving 1x behind. And so we're going to end up with another limit as n goes to infinity of, so we had an n plus 1 left over from the factorial, we had an x left over from the x's, and we had a 5 left over from the 5s, and we want this limit to be less than 1. Now, where we run into the issue here is that initially, when we let n go to infinity, this limit goes to infinity. And that's true, except in one particular case. When x is any number but 0, then yes, this thing will go to infinity. But when x is 0, or if we had a term like x minus 1 or something like that, then when x was equal to that constant, then if this x is 0, then this whole expression is 0, and the value of n doesn't matter. And so the interval of convergence is actually just a single point. It's at the point 0, and therefore the radius of convergence is also 0. And again, that's just because when x is 0, every expression in this sum is 0, 0 plus 0 plus 0 plus 0 forever. And adding up zeros, no matter how many of them, you still are going to end up with 0. But if x is any other value, then you're going to be adding up a finite value that's getting bigger every single time forever. And so it only converges at 0. So that is our first case. And that's kind of an important one to kind of keep in mind. If you have n in the numerator, then you have to think about, okay, well, is there any place where I can make this 0? And for a power series, there is going to be one value. There are no cases that I'm aware of where even the 0 is overcome. And I can't think of why it would ever happen. All right, so let's look at our second example. Now, since I have no factorials in this, I could use the root test if I wanted, and I'm going to go ahead and do that. N goes to, now if you use the ratio test, it will work exactly the same. So you'll get exactly the same answer. But since this is n to the n, this is the one case where I feel like the algebra for the ratio test is just a little bit harder. And so doing the root test is going to save me a lot of trouble. Technically, these are absolute values under the square root here. Because you need the expression to be positive when you take an even numbered root. So, but when we cancel our powers of n, we end up with the limit as n goes to infinity of x minus 2 over n. And again, there's technically absolute values in here, but and we want this to be less than 1 for our, just like with the ratio test, for this to converge. But in this case, n is in the denominator. And since n is in the denominator is going to infinity, which means that the entire expression is going to 0. So it's always going to be less than 1. So since the limit is 0, and therefore it always converges, the interval of convergence is all real numbers. It's negative infinity to infinity. And the radius of convergence is also infinity. So, and in the denominator, that's good for convergence. It converges everywhere. And in the numerator, when you're done doing your either root or ratio test, that's bad. That means it only converges at a single point. And then the third case is, again, the one that's a little bit more involved. In this case, there is only one point, and we already know what it does. In this case, there are no endpoints because we're looking at infinity. But in the third case, what we end up with is a interval of convergence that has a finite length. And so it's going to have finite endpoints and that are not a single point. And so we're going to have to check not only the open interval of convergence, which we're going to get from the root or the ratio test, but then also the actual specific endpoints to see if either of those values on the end is going to converge. So it's a little bit more involved when we have sort of the typical case. Now, again, in this case, we can do either the root or the ratio test. It's very common to do the ratio test, so I will just continue with that tradition. But this one would also be totally fine to do with the root test because there's no factorials. So this would be n plus 1, x to the n plus 1 divided by 3 to the n plus 1, and then times the reciprocal 3 to the n over n x to the n. And then canceling things, we would end up with the limit as n goes to infinity of, well, we would have n plus 1 over n. Those don't technically cancel. And then x to the n plus 1 and x to the n would leave me with an x, and 3 to the n plus 1 and 3 to the n would leave me with a 3 left over. Now, what you can do here is you can do the limit of each piece of these separately. And so we can put a times in between the limits and take out the x plus 3 here and take out the n plus 1 here. And when the limit as n goes to infinity of n plus 1 over n, there's a bunch of different ways that you can analyze this algebraically, but essentially what it means is that this limit is actually 1. And in this case, we want, so 1 is not going to do anything to us. And this one, we need this expression to then be less than 1. So this is just going to be equal to this. And so there's no n's in this. So it's just the absolute value of x over 3 that we want to be less than 1. Now, from this point, then, we're going to pull out this inequality and we're going to solve it in terms of x. And the first thing we have to do is take out the absolute values. So this is going to become -1 is less than x over 3 is less than 1. And then from there, multiply everything by 3. So we get -3 is less than x is less than 3. Now, it's very tempting to like quit here. And sometimes this is in fact the answer, but sometimes this is not in fact the answer. And it is important to check. Developing an intuition about these things is useful, but you still have to show the work. So what we have to do is we have to now check the endpoints of the interval to see if the interval will converge, the series will converge at -3 or 3, or possibly both, or maybe neither. Because there are different things that can happen. You could end up with an open interval like this. You could end up with a half open, half closed interval, or you could end up with a fully closed interval. And we don't know without doing the check. So we're going to check x equals -3. And for that, we're going to go back to our original power series. And we are going to replace x with -3. And that is going to leave us with n equals 1 to infinity of n and -1 to the n, because of course -3 is -1 times -3. The 3 to the n cancels with the denominator, and so we're just left with the negative component. This is -1 +1 -1 +1 -1 +1 -1 +1 forever. This doesn't blow up, but it also doesn't converge. At this endpoint, by the divergence test, or sometimes it's called the nth term test. Because if you let the limit of this term go to infinity, as n goes to infinity, this term is going to go to plus and minus infinity, depending on whether you're at an even term or a positive term, because the n is in the numerator. And then we do the same thing. We check at the other endpoint, check at x equals 3. And the only difference that we're going to have here is we're going to have a 3 to start with. And so when this converges, or when the 3's cancel, we're just going to be left with n. And this also fails to converge for the same reason. So neither endpoint converged. So that means that the interval of convergence is -3 to 3. And the radius of convergence is 3. How do I know it's 3? Well, there's a couple places where you can tell that it's 3. So for instance, here, even if you have x minus 2 or something like that, you get a point where you've gotten a linear factor of x, and then both endpoints are plus and minus versions of each other before you add the constant. So that's one way. The other way is that you can just use the endpoints. The length of the radius of an interval is going to be basically b minus a over 2. And so in this case, we have 3 minus a -3 over 2, which is 6 over 2, which is 3. Now, you can always, once you get the radius of convergence solved for x, you can always do this. It's half the length of the entire interval. But usually there's a point in the calculations where it becomes somewhat clear what the value is. But you do have to be a little cautious, because if you have something like 1/2 x plus 3, or 3x plus 4, or something like that as your expression raised to the n power, then it's not going to be quite as obvious, and you might as well just do the math, get to your final interval, and then do this calculation. Now, for these power series convergence problems, you're going to do a lot of ratio tests. You're going to do a lot of root tests. The other series tests are going to come into play when you test these endpoints. So you may end up with a p-series, or you may end up having to do a limit comparison if it's very complicated, though that's somewhat unusual. P-series, alternating series, those are much more frequent occurrences when you get to the end. But of course, it does depend eventually on what the specific series was that you're testing as to how your expression is going to simplify. But it's at the endpoints where you're going to use those other tests of convergence.